Next, we are going to discuss about the shifting theorem second. So for that, we need some basic definitions. So one is the unit step function. So the unit step function or Heaviside function is defined as like that ht is equal to 0, 1, and t less than 0 and t greater than equal 0. This is also known as the unit step function. So this function is unit step. So here is t. So see that t is less than 0. T is less than 0, it is 0. So therefore this is, and t is greater than equal 0, this is 1. So this is the unit step function and it is denoted as u or u0t. So to highlight that, 0 is the have the jumping discontinuity. Now if the jumping discontinuity is in any other point, not in 0, then how we can write it? So this can be written as ht minus a ut minus a. This is 0 when t is less than a and 1 when t is greater than a. And it is denoted as u a. And this is very important to get the Laplace transform. So now we can express these functions when you have given with the unit step functions, how we can rewrite this function. So from the definitions we have, this u pi t is equal 0 when t less than pi and 1 when t is greater than equal pi. So therefore e to the power t is multiplied. So it can be written as like this form. So when some function is given in this form, then we can convert it to with the unit step function and then we can calculate the Laplace transform. Now there is another example here, uat minus ubt. So this is 0 when t less than a, 1 when a less than equal t less than equal b, and 0 when t greater than b. So it can define like this. This is t. And let's say this is a, and this is b. So this uat is means this is 0 when u less than a, and this is 1. So this red color is u a, and then we take a different color, this color. So this is ubt. This color is ubt. So now look on this. When less than a and less than a, then both are 0. So therefore their subtraction will be 0. So this is that. Now between a and b, ua is equal 1, but ub is equal 0. So therefore their subtraction is 1. And when t greater than b, then both are ua is equal 1, ub is equal 1. So therefore their subtraction will be 0. Next, we have our statement of the shifting theorem, second shifting theorem. And this says that if Laplace transform of ft is equal to fs, then Laplace transform of ft minus a uat is equal e to the power minus as fs. So ft minus a uat equal e to the power minus as fs, where a is any real number. So now example here, Laplace transform of gt, where gt is given as gt is equal 0 and 0 less than equal t less than equal 5, t minus 5 whole square when t is greater than equal 5. So how we can solve this Laplace transform of this function? So we will use the help of the unit step functions and we will see that. So we can rewrite gt as t minus 5 whole square u5t. Okay. So now if we take it that this function is ft minus a is equal t minus 5 whole square, then we can use this formula and we can solve this Laplace transform. So we assume that ft minus 5 equal t minus 5 whole square. Clearly a is equal 5. So if ft minus 5 equal t minus 5 whole square, then what will be ft? Ft will be t square. Just replace it. So therefore, if you know ft equal t square, then what will be fs? So we need to calculate fs. So what is fs? Fs will be 1 over s to the power 3. Sorry, 2 over s to the power 3. This is fs, which is the Laplace transform of ft square. So therefore, the combined Laplace transform will be means the gt is equal t minus 5 whole square u5t is by this formula e to the power a is here a equal 5. So this is equal e to the power minus 5s fs. So which is 2 e to the power minus 5s over s to the power. We have our next problem is Laplace transform of t square u4. So to solve this Laplace transform, so we'll again know get the ft. So let's gt is equal t square u4t. Then ft minus 4 equal t square. So this implies ft is equal t plus 4 whole square. So which we expand it. So for the Laplace transform, so Laplace of ft will be Laplace of t plus 4 whole square. So now t plus 4 can be written as t square plus 18 plus 16. Just extend the power. Then we will take the Laplace transform by linear property. We can separate them, and Laplace of t square equal 2 over s to the power 3. Laplace of t is 1 over s square and multiply by 8, and Laplace of constant is 1 is equal 16 over s, and that is our s. Then we apply the formula for this Laplace transform. ft minus 4 is equal u4t, so which is equal e to the power minus 4 is fs. So here ft minus 4 is t square, so this is the formula. So e to the power fs we already calculated, so therefore we just substitute it for fs and we got the answer is e to the power minus 4 is over multiply this. Now we have an inverse using the shifting theorem, and here we have again compare it with this formula. Just recall this formula. So e to the power as fs. So now compare this one. So what you will get it here, s is equal. So you will get s is equal pi over 2 and fs is equal 1 over s square plus 4. So now the inverse of this one is L inverse 1 over s square plus 4 is this is half sine 2t. And then we have here, this is we take as ft, and then the whole Laplace transform is equal ft minus pi over 2 because t minus a and uat. So a is equal pi over 2. So therefore ft minus pi over 2 u pi over, and then you will get it here half sine 2 here because it is sine 2t. So half sine 2 t minus pi over 2 u pi. So if we further simplify, then you will get it here. Sine 2t minus pi u pi over 2 half sine 2t minus pi. So we can take out the minus and it will be sine pi minus 2t, and sine pi minus 2t is half sine 2t u pi over 2t. Because pi minus 2t is pi minus something, means it is in the second coordinate. So it will be plus, and as pi minus theta equals sine theta, so it will be sine 2t. So the answer is minus half sine 2t u pi over 2t. Now our next lecture is differentiation and integration of Laplace transform.